from the Ohio State University, and her talk is titled Stability and Control of Walking at Various Speed Slope Combinations.
Thank you, Adam. My name is Alwan, and I'm a PhD student at the Mechanical Engineering Department at Ohio State. And I'll be presenting my work regarding investigating stability and control of inclined walking for healthy subjects. So walking, sorry, let's see, I think it jumped. All right, so the motivation for my work is that 1 in 4 older adults report falling each year. So falls are a leading cause of injury-related deaths, especially for older adults that are 65 or older. So by understanding the mechanics, energetics, and cognitive behavior of human movement, we can hopefully predict fall better and consequently lower the risk of falls by designing better assistive devices, prosthetics, and exoskeletons. Our work also impacts fields such as robotics and rehabilitation. So why study sloped walking specifically? As you may know, slopes are often used as an alternative to stairs for special populations such as the elderly, lower amputees, and people with lower limb deficiencies. And such tasks can be challenging, especially that muscles need to generate more power to the legs when walking uphill. So hundreds of papers exist on level ground walking, but unfortunately few of them focus on the control and stability of walking on slopes or uneven terrain. So walking is not perfectly periodic, even on a treadmill. Small perturbations usually generate from muscle and sensory noise as part of natural variability. Those sort of perturbations actually increase with aging, and we know that from previous research. So how do humans recover from these deviations? There are a couple of ways. One is foot placement modulation in the direction of the perturbation. So for the second video here, you see that the experimenter is changing belt speed to basically simulate slips or trips. And to recover from such perturbation, the subject is placing their foot in the direction of that deviation. In the first video on the top, you see subject running, and this is another way of recovering from deviations, which is like applying more leg force or push-off impulse modulation. So here we will investigate control strategies of healthy adults. We will investigate the control strategies that healthy adults use when walking on uphill slopes to stabilize their gait. So the first part here, I will present to you the experimental analysis. Our lab uses equipment such as motion capture system, an inclined treadmill, and reflective markers. We collected data for 10 subjects, 4 females and 6 males, for 2 minutes each trial. We have collected 12 randomized trials for 3 speeds, 0.7 meters per second, 1 meters per second, 1.3 meters per second, as well as 4 different inclinations, 0%, 3%, 6%, and 9%. For the purposes of this presentation, I will only be presenting results from 1.0 meters per second and results from the left-to-right transitions, which we know that are mirror symmetrical to right-to-left transitions. To infer control, we use linear regression methods. We define foot placement gains as output over input, or in other words, the coefficients of the following linear models. So in the first function here, or the first linear regression here, you see that the output is the sideways foot placement, and the input are the hip states in the sideways, fore-aft, and vertical directions, the positions, and as well as the velocities. In the second equation, you see the fore-aft foot placement equation, which we use the four-act foot position as the output. And again, the hip states are as input. So in the video here, you see that we're pulling the subject sideways from either side, and the subject is recovering from such perturbation by placing their foot in the direction of the pulling or the perturbation. So what does that mean for us? That tells us that deviations of foot placement from the average values can be explained by deviations in the pelvis position and speed from average values at mid-stance. So from our results here, I'm showing on the left side the response of sideways foot position responds to sideways hip position for the lowest inclination, the 0%. On the right side, you see the same information for the 9% inclination. Within each plot here, you do see a spread, and the p-value is significant. And that we know from previous studies is that the hip foot position is explained by deviations in hip positions. However, when we did t-test between both of these values or both of these plots, we didn't see any significance. And similarly for the four-act foot placement, we did not see any significant from the lowest slope and the highest slope. Sideways hip states slightly increase with steeper inclination, but not significantly. So in this plot here, on the x-axis, I show the number of steps. On the y-axis is the sideways hip position deviations, delta x hip. And each column here, you see a different inclination that the subjects were asked to walk on. So let's compare the 0% to the 9%. You do see a little bit of a spread, but it's not that significant. Similarly, for sideways hip velocity deviations on the y-axis here, you do see more spread as we increase inclination, but it is not significant. We also see a similar trend for four-act hip velocity. We also quantify stability by calculating flow gait multipliers. Flow gait multipliers are 3-state variables that tell us how quickly small deviations are corrected. So if the number is less than 1, then the system is stable. If the number is greater than 1, we know that the system is unstable. The way we calculate it is by calculating individual step-to-step mapping from each transition. And multiplying those individual mappings will give us a full point Cray map. Taking the eigenvalues of the full point Cray map will give us flow gait multipliers. So here you see the equation that's showing inputs and outputs linear regression and the Jacobians as a function of that. So flow gait multipliers for our specific experiment show a little bit of trend towards instability, especially for flow gait multiplier 3. We see a little bit of trend, however, not very significant. And the overall number is still less than 1. So you see the highest is about 0.35. So the system is still overall stable. The second part of my study is building a data-derived feedback controller, and this work is in progress. We simulate the human body as an inverted pendulum biped model. So the body is represented by a center of mass with massless legs, and in between the push-off and the heel strike phases, we represented by an inverted pendulum. So using experimentally derived linear models of coefficients, we can modulate the magnitude of the push-off and the step length to keep the biped stable. Such methods will help us simulate sloped walking for different inclination values and detect when the controller becomes unstable. And then we can modulate the input to make the controller become stable again. So my hypothesis is that for much steeper inclinations, we may find that the controller becomes highly unstable. Future work can include conducting walking studies with healthy adults in comparison with older adults for different types of everyday tasks, including slopes, uneven terrain, unexpected obstacles, external forces, and so on. We can also build a comprehensive predictive model of walking that can encompass different robust adaptive control stability properties of young adults versus elderly by considering multi-body dynamics, different body segments, and not just simplified. We can also consider energy expenditure and muscle forces that result in certain gait behavior, especially that we know that humans walk in a manner to minimize effort. I'd like to give thanks to Wang and Srinivasan, who is my advisor, and Nidhi Sitapathy, who is a current postdoc at University of Pennsylvania. And I'm open to all questions. Thank you.
All right, thank you so much. That was a wonderful talk. I really liked your simulations at the end, and your future directions seem like a good, like they're really building on nicely from the data that you've recorded. So if anyone has Q&A or questions, rather, you can post them in the Q&A. I wanted to just go back to your future direction. We do have one question that's come in. How do you expect your results to change from uphill to downhill?
So unfortunately, because of limitation of our treadmill, we did not collect downhill results. But we can probably say that step length will change with downhill. As intuitively, I would say that when walking uphill, you would increase your step length. But then when walking downhill, you would decrease your step length. And step length is controlled by foot placement. So that would change.
Great. Yeah, your point here, which is about everyday tasks. I was just wondering if you had any sense of what falls look like, or like what instability looks like in older adults when they're walking up in slopes in everyday tasks. Has that been looked at generally in like a rehabilitation setting, or anything like what a hallmark of a fall on a slope, what might precipitate a fall on a slope in an older adult?
So there are a lot of reasons why older adults fall. So when they fall on living ground walking because of higher instability, because of like neural noises. If you are trying to make that task more difficult for the subject, especially for older populations, they may need like to generate more power to walk up a slope. So the noise can increase even more when they're trying to achieve such a task.
Okay.
So it's not well understood, and this is why I started with this project in the first place.
Yeah, that's really, I think it's really interesting work. And so it makes sense why you'd go down this road if there's not so much research that's been done there yet. We did have another question come in the chat. Have you thought about implementing your model in bipedal robots?
Not currently, but that's definitely something that I can think of in the future.
And okay, cool. And then last question, and then we're gonna have to wrap up the session. Do you think it's possible that foot placement strategies are impaired in older adults?
Yes, that's definitely a possibility. Especially that, healthy subjects can use foot placement to modulate their walking or to recover from deviations and perturbations and even external forces, but older adults cannot do that, and that's can definitely be affected.
Cool. And then just so you know, the person who asked that question has just suggests checking out 2 recent papers. So you might want to just open up the Q&A just to make sure you can have a look at that. So with that, I think that we'll wrap up this session. Thanks everyone for your questions, and thank you.